Hello, and welcome to our fourth video entitled Any Way You Slice It, otherwise known as Areas of Sectors, Segments, and Annulus. So what is a sector, a segment, and an annulus, you ask? Well, let's take a moment and define them. So a sector of a circle is essentially a wedge-shaped piece, as outlined in this gray area here. Formally, it is defined as a region of a circle between two radii and an arc. A segment of a circle is defined as a region between an arc and a chord. A segment of a circle kind of looks like you made a straight cut just across. You might even consider that to be like the crust of a piece of pizza, perhaps. And an annulus is the region between two concentric circles. The informal name for an annulus is just a ring. Right? One thing that you're going to need to keep in mind as we work through these is that we're going to keep all of our answers in exact form. And so that means that we're going to leave it in terms of the pi symbol. We're not going to convert that to the decimal approximation. Each of these regions represents a different portion of the area of a circle. We're going to focus on each of them individually. So let's take a look at a sector first. A sector is really just a portion of a circle, and if we want to figure out what fraction of the circle that is, we can look at the arc measure, which remember is exactly the same as the central angle measure, and we can determine a fraction of that central angle measure compared to the 360 degrees that are in a complete circle. That fraction multiplied by the area of the circle gives us the area of the sector. So the formula for calculating the area of the sector can be thought of as the fraction of the circle multiplied by the area of the circle. And remember that we're going to leave our answers in terms of pi in exact form. So let's actually see this in action. Right, to find the area of this sector, remember it's the measure of the central angle, which I'm going to call A, over 360, multiplied by pi r squared, which is the area of a circle formula. So in this case, we have 40 over 360, and we're going to multiply that by pi times the radius squared. Well, 40 over 360 reduces down to 1/9. 9 squared is 81, so we have 81 pi. Oops, 81 pi. And then 1/9 of 81 pi is simply 9 pi. Since our initial unit was centimeters, our area will be in square centimeters. So here is our final answer. The area of that sector is 9 pi square centimeters. Here's one for you to try. Why don't you pause the video while you calculate the area of that shaded sector? Welcome back. Here's a solution to the problem. Did you get it right? Now we're ready to examine how to calculate the area of a segment of a circle. But before we do it, I want you to look at the picture equation that was provided for you. Essentially, the area of a segment is exactly the same thing as the area of the sector, which is here, minus the area of the triangle, and that's going to give you the area of the segment. You'll find that the picture equations are kind of helpful for a lot of you, but if you're not into picture equations, then you can also think about this as basically sector minus triangle. Let's see how it actually works. Okay, we're looking for the area of this segment of a circle. I want you to notice that the central angle has a measure of 90 degrees. And remember, because both radii are congruent, that this is also 6 centimeters long. So we're going to do the area of the sector And from that, we're going to subtract the area of the triangle in order to get to the area of our segment. So let's deal with the sector first. The sector is here, and it comes from here out and then bounded by that arc. So to find the area of my sector, I have to do the measure of my central angle, which is 90, over 360. That gives me what portion of the circle I have. And then we're going to multiply that by the area of the circle, which in this case is 6 squared pi. So I'm just going to write that as 36 pi. From that, we are going to subtract the area of my triangle, which I'm highlighting here in green. Okay, since these two legs of the triangle are acting as both the base and the height, the area of my triangle then is 1/2 of the base, which is 6, times the height, which is 6. Now I have to simplify both expressions, so I end up with 1/4 of 36 pi, which simplifies down to 9 pi. And from that, I'm going to subtract 1/2 of 36, which is 18. So your entire segment has an area whose expression is 9 pi minus 18, and don't forget your unit, square centimeters. Now I want you to try one, but this one's a little bit trickier because we're not dealing with a central angle that's a right angle. So before I turn you loose on your own, let's kind of think about this for a second. I need the height of that triangle, which is there. Drop that altitude. And so you're going to need to use your special right triangle relationships to figure out what the length of that altitude actually is. And remember, because these two radii are congruent, the original big triangle is an equilateral triangle, so you do know the base length here is also 3 centimeters. So armed with that knowledge, go ahead and see if you can calculate the area of that segment of the triangle. Here's the solution to that problem. Here's the area of the sector, central angle, divide by 360, multiplied by area of the circle. Here's the area of the triangle. There's 1/2 the length of the base times the height. Notice again that I had to use my special right triangle relationships to calculate that height before I could actually find the area of the triangle. Simplify both expressions and don't forget your unit. For our third type of area calculation, we're going to learn how to calculate the area of an annulus, which is commonly known as a ring. If you think about it, if you had a circular plate, and you cut out the inside of it, right, you'd end up with a donut, right? And you get the area of that donut by taking the area of the big circle and subtracting the area of the small circle from it. When you take that small circle out of the center, it leaves this ring portion. So the area of an annulus can be thought of as the area of the big circle minus the area of the small circle. Notice in the formula that the capital R represents the radius of the big circle, and the smaller circle's radius is represented by a lowercase r. So that way it helps you keep track of which one is which. So let's work with an example of this problem. So in this case, you're told that the radius of the larger circle is 12 centimeters. The radius of the smaller circle is 8 centimeters. So if we're doing the larger circle area minus the smaller circle area, then we're really talking about pi capital R squared minus pi little r squared. So capital R in this case is 12. So we end up with 144 pi. And my smaller radius is 8. 8 squared is 64, so that gives me 64 pi. And if you have 144 pi, take away 64 pi, that's going to leave you an area of 80 pi square centimeters for the area of that annulus. Okay, here's one for you to try. The radius of your larger circle is 12 centimeters. The distance x is 3 centimeters. You need to find the area of the shaded region, which in this case is the annulus in question. one thing you want to consider is that if this distance x is 3, then can you actually figure out what the smaller radius value is? So again, pause this video and give it a shot, and then we'll check in with you in a minute. So here's the solution. Did you get it correct? You should have figured out that the radius of the smaller circle is 9 centimeters. You get that because the big circle is 12, take away the 3, that gives you the 9. So the annulus area is the area of the large circle, which is 144 pi, minus the area of the smaller circle, which is 81 pi. That leaves 63 pi to represent the annulus area. This last example represents a working backwards problem where instead of actually calculating the area, you're asked to find the measure of the central angle. So remember that the area of a sector, which I'm going to call capital A, is equal to the measure of the central angle divided by 360 multiplied by the area of the circle itself. So using that formula, let's go ahead and fill in what we actually know. So we know that the area of the shaded region, meaning the area of the sector, is 14 pi. So that has to be equal to the measure of the central angle, which I don't know what that is, over 360, multiplied by the area of the circle itself. Well, the radius of the circle is 6, so the area of the circle is 36 pi. We can do a little bit of simplification here. 36 goes into 360 10 times. And if you divide by pi on both sides of this equation, then those pi's are actually going to cancel out with each other. And so we're left then with 14 is equal to x over 10. So to complete this equation, we multiply both sides by 10. And so clearly the measure of the central angle must be 140 degrees. Here's one for you to try. This time the sector's area is 2 pi square centimeters. The circle's radius is 4 centimeters. Find the measure of the central angle, which is indicated by x. Take a moment, pause the video, and when you come back, you'll have the solution to check. Welcome back. Here's the solution. X turns out to be 45 degrees. All right, and remember, just very quickly, that the area of the sector is the central angle divided by 360 multiplied by the area of the circle itself. So if we plug in all of our known values, here I actually divided both sides by 16 pi to get to my next step here. So I have 2 pi over 16 pi equals x over 360. The left-hand side of this equation reduces down to 1/8. So you have 1/8 equals x over 360. Solve that, you end up with 45 degrees. So just to sum it up, the area of a sector can be calculated by taking the measure of the central angle and dividing that by 360. That gives you the fraction of the circle that you have, and then you multiply that by the actual area of the entire circle. A segment of a circle can be calculated by taking the sector and subtracting the area of the triangle, and the annulus is calculated by taking the area of the big circle and subtracting the area of the small circle. Hope this video helped, and look forward to practicing any way you slice it.